Okay, welcome back to another episode of How to Algebra, where I show you the fundamentals of algebra. Okay, so we are looking at exponential growth and decay. We have a couple of word problems, and then we go through the transformations of the graphs for exponential functions. All right, so let's get it. Okay, exponential growth and decay. I think it's best if we start with a couple of examples of what an exponential function looks like. So y equals 2 to the x. So 2 is the base, and the exponent contains the variable, right? X is in the exponent. Now, every exponential function, as long as it's not shifted, translated left, right, up, or down, will have 3 key points. Even if it is shifted, it'll still have these 3 key points, but we'll talk more about that later. The 3 points are going to be 1, a, 0, 1, and -1, 1 over a. Again, a being the base. So for instance, 2 to the x, 2 is a. So if we follow our little formula, our 3 key points are going to be 1, 2, 0, 1, -1, 1 over 2. And then we could also find, other points, right? Like when x is 2, so 2 to the second power would be 4, right? 2 squared. So if we plot these points, we're going to see that -1, 1/2, 0, 1, 1, 2, and 2, 4. Exponential function. So rises to the right. This is growth, right? It's coming from the left, and it's getting infinitely close to the x-axis, but never touches the axis, right? And it's y equals 0 is never the case. It's never the case. So it's always positive. Which brings us to domain and range, right? The domain is all real numbers. The range is from 0 up to infinity, right? Because it can never be 0. It can be anything bigger than 0, literally. Unless it's shifted down, then that's another topic. 3 to the x. Again, the base is 3. So our points of interest, our key points rather, are going to be 0, 1, right? Every exponential function will have this. 1, a, so 1, 3. And then if we want 3 squared, right, when x is 2, y is going to be 9, right? Because 3 squared is 9. And then -1, 1 over 3. All right, so looking at the graph, -1, 1/3, 0, 1, 1, 3, and then 2, 9. All right, so the domain and range for this one, domain is still all real numbers, right? X could be anything from -infinity to infinity. And the range is going to be from, again, 0, not including, up to infinity. All right, the third example, we have 0.5 to the x power. So our a value is 1/2. Okay, 0, 1 is definitely in our set of numbers. 1, a, so 1, 1/2. If we wanted 2, for instance, this would be 2, 1/4. Right? Square the top, square the bottom. 1 squared and 2 squared. And then -1, 1 over 1/2, which we know when we have a compound fraction, right? We keep the top, change the multiplication, flip the bottom. So this is basically 2. So if you notice, this is going to look like, so we have -1, 2, 0, 1, 1, 1/2, 1 1/4. And it's going to keep falling down all the way towards the x-axis, but never touching the x-axis. All right. So when it rises to the right, this is known as growth. When it falls to the right, this is known as decay. Over time, right? Decay. And the domain for this is all real numbers, and range is going to be the same. Anything from 0 all the way up to positive infinity. Okay. The general form of an exponential function is y equals a b x. So what this is basically a is some initial amount or value, initial value, initial amount, and b is going to be your growth or decay factor. And x is over some time, right? Typically years. So these are the 3 variables that are in the general form. Now, it doesn't necessarily have to be an initial amount, right? It could just be a problem with just a number, but typically you have word problems associated with these types of problems, and it's going to be some initial amount. So it's kind of a foreshadowing idea. Okay, so some examples of what growth and decay are going to look like, and then we always figure out what is the percent increase or decrease, which we'll talk about that in a second. All right, so in the first example, we have y equals 1347 and then 1.73 to the x. So let's look at all the b values, right? Because b is what's going to tell us if it's increasing or decreasing, or if it's growth, which is increasing, or decay, which is decreasing. So if b, right, so I guess some side notes. If the b value is greater than 1, then this is growth. And if b is in between, right, 0 and 1, so if it's less than 1, then this is known as decay. And you always want to compare the b value to 1. So for instance, what I'm saying is, if this line represents 1, right, 1.73 is obviously going to be higher up. 1.73. So the growth, like the difference in the two numbers, is 0.73. Or in other words, 73%. So we like to deal with decimals as opposed to percentages, especially in like the calculator or any kind of calculation. It's always best to deal with the decimal. So with that being said, this first example is growth or increasing. And at what percent? Well, we just said 73%. Switch the colors up. All right, the second one, we have 1.5. Again, we want to compare this to 1. So obviously it's bigger than 1. So it's going to be increasing. And the percent that is increasing is 50%. Right, because that's how much bigger it is than 1. The next example, 2 times 0.065 to the x power. So 0.65 in relation to 1, it's obviously less. So this is decreasing or decay. And you say, by how much? Now, if you think about it, looking at the little chart to the right, 0.65 is less than 1. And you say, okay, well, by how much less? Right? How much did it go down? And it actually goes down 0.35. Right? That's the distance. If you start at 1 and you count down to 0.65, you would have moved 0.35 or 35%. So it's decreasing by 35%. All right, the next example, we have 3/4. 3/4 is less than 1. Decreasing. And decreasing by 25%. It's worth noting that when you have a fraction, it's so easy to be like, oh yeah, it's decreasing. But you always want to like take a moment and just make sure that the fraction you're looking at is actually less than 1. And the way you do this is when you have a fraction, the bottom number needs to be bigger. If the bottom number is bigger than the top number, the denominator is bigger than the numerator, then it's less than 1. It's decreasing. But if for some reason you have a fraction and the top number is bigger, that's growth. Just keep that in mind. Okay. 1/2. This is less than 1. Decreasing. And by 50%. All right, last example. 6 to the x. You want to compare 6 to 1. 6 is obviously bigger than 1. So this is going to be increasing for sure. And you say, by how much? Well, it's 5 bigger, right? 6 is 1 plus 5. So 5 whole ones. So this would be an increase of 500%. All right. Let's look at some actual examples. So example number 1. All right, student enrollment of Reagan High School was 2,100 in the year 2000. It has increased by 6.5% per year since then. If this growth continued, and if we didn't open Johnson High School, what would the Reagan enrollment be in the year 2015? All right, so a couple of things. Let's extract some information here. So there's 2,100 students in the year 2000. So this is definitely our initial amount. It has increased. So this implies growth. So immediately I'm thinking that my growth factor is definitely bigger than 1. How much bigger than 1? Well, 6.5%. And we want to know what's it going to be in 2015. So this is like the time. All right. The initial amount, 2,100. The factor, the growth factor, B value, is 6.5%, which if we move the decimal 2 places to the left, this will give us 0.065. But we want it to be growth, so it has to be bigger than 1. So we're going to add 1. And then X is time, right? From the year 2000 to the year 2015 is 15 years. And Y is our total amount. So we set our problem up. We're going to get 2,100 times 1.065 to the 15th power. Okay, you put this in the calculator, you're going to get roughly 54 point something. Whatever it is, you can't have, right, because this number represents people. So you can't have a portion of a person. So that this number will definitely bump up, round up to 5,401. I believe it was like 0.66 if I remember correctly. But again, you can't have partial people. So you always round it up. 5,401. Okay. Second example. Miss Eddie bought a car for 32 grand. The car begins to depreciate, right? Depreciate the moment she drives off the lot and continues to depreciate at 20%. So depreciate is another word for decay. 20%, this is our factor. And 32K is going to be our initial amount. And we want to see what the car will be worth in 6 years. So this is our time. Okay, 32,000. That's our initial amount. The factor, since it's depreciating, it's decaying by 20%, will be 0.8. Right, it has to be less than 1. So 0.8. And 6 years. So our setup, 32,000 times 0.8 to the 6th power. Put this in the calculator. We're going to get $8,388.61. So that's the car depreciating 20% a year. And after 6 years, that's what it's going to be worth. It's kind of sad, actually. Okay. So that's as far as we got with the word problems. So let's look at some transformations. So again, every parent function or every exponential function will look like the parent function here. It's going to have this general shape. And you're always going to have the 3 key points. Right, this is 1 comma a, this is 0 comma 1, and this is going to be -1 comma 1 over a. Right, that's just the way it is. All right. If we look at the first example, 2 to the x, the negative reflects across the x-axis. So this is going to flip it down. One way to think about this, so if we do our key points, well, here's the parent function first. All right, there's the parent function. We're just going to reflect this across the x-axis. So every key point gets reflected. Okay. This is what it would look like. All right, 2x minus 3. So this is going to look like the parent function, except translated down. I guess we could talk about the domain and range real quick. So on the left, the domain, it's always all real numbers, right? Any real number can be plugged into this and a real value will come out. However, the range is going to be starting at 0 and then going down. So -infinity to 0. Number 2, it's the parent function shifted down 3 units. So here's the horizontal asymptote, right? Since there was no shift in number 1, the horizontal asymptote was at y equals 0, right? That's always where it is. Now, since we're shifting it down, horizontal asymptote's at y equals -3. And then all the key points are going to be shifted down 3 as well. So it was normally at 1/2. It's going to go down 1, 2, 3. 0, 1 is going to move down 3. And then the 1 comma 2 is going to move down. So here is the rough sketch. Domain, all row numbers. The range is from the horizontal asymptote up. So -3, not including it, all the way up towards infinity. All right, 2x plus 3. So this x plus 3 business, this is going to shift it to the left 3. Right. So if you remember, anything next to the x, the inside lies. Right. It's always opposite of what you think. X plus 3, it gives you the feeling it should go right because it's a plus, but it's actually the opposite of that. So this is going to be, our key points. All of our key points are going to shift left. So 0, 1, 1, 2, 3, 1, 2, 1, 2, 3. So there it is. It's shifted to the left. Here it's worth noting that let me draw the parent function next to it so you can, I guess, get an idea. All right, so here's the parent function in black. Translation is in red. So it shifts left. Domains all row numbers. The range is always 0 to positive infinity. Okay, it's not in here, but it's worth noting that if I wanted do it in blue. If I wanted 2 to the negative x plus 3, right, the negative that's outside of the parentheses, what does this do? Normally we know that it'll typically reflect it across the x-axis. The y-axis. It's going to reflect it across a vertical axis for sure, but not the y-axis. It's actually going to reflect it across the middle key point, the 0, 1 point. The 0, 1 point, that's what it's going to reflect it across. Now, in this case, the 0, 1 point got shifted left. So it's going to reflect it across x equals -3. So the thing to note there is that it reflects it across that middle key point. Just a little FYI. All right. And then the last example we have. Okay, so what's this going to do? This is going to shift it to the right. So this is going to be to the right. This is going to be up. So to the right 4, up 6. And then we're going to reflect it down. So I guess one thing to note, I guess going back to the first example, here in this case, the negative reflects it across the x-axis. Well, I guess the x-axis is appropriate because it didn't get shifted up or down. But in general, I don't think the x-axis is good because it's going to reflect it across the horizontal asymptote. That's, I guess, more accurate. Horizontal asymptote. So this y equals 0 line. So what I'm saying is that for 4, it's going to reflect it across y equals 6, right? Because the horizontal asymptote is going to get shifted up. 1, 2, 3, 4, 5, 6. So here's y equals 6. This is the horizontal asymptote. And we know that it's going to be reflected down. So let's look at our key points. So our key points are going to be, so I know 0, 1 is one of them. It's going to go up 6, and then right 4. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And then it's going to reflect across. All right. Then our points are typically like this. So this is basically what it's going to look like. The domain is always all row numbers. The range in this case is going to be from the horizontal asymptote down. So I know it's going to go down towards negative infinity and go all the way up towards the horizontal asymptote, which is 6. Not including 6, so it gets the parentheses. Okay, I think that is it for growth and decay. The next video will be compound interest. So please subscribe, like, comment, hit the thumbs up button. Let's get the algorithm going. So until next time, peace.